Yeah, good afternoon, participants. Welcome to the fifth day of ATAL AICT Faculty Development Program on Machine Learning for Interdisciplinary Engineering and Applications. I hope you have enjoyed the past sessions. Especially, we had a very interesting session yesterday from TCS by Rajiv Arvat. He was trying to introduce the tools and recent excitements that is happening in this area. And today we are very happy and uh, very excited to introduce uh, a person who actually trained by our department, and we are very proud of him. Uh, After acquiring PhD, he has got a good position in Sony, which is a well-known and renowned company. Dr. Anil Raj J. So he will be talking about applications of ML, machine learning, and deep learning in pertaining to electronics engineering. So he is the right person to talk this subject. He is well trained in this area. So I'm very happy to introduce Dr. Anil Raj, and I request Preena to formally say a welcome and introduce the speaker to the audience. Over to Preena.
Good evening, all. Today's speaker, Dr. Anil Raj J, is presently working as an artificial intelligence research engineer in Sony, Bangalore. He has his BTech degree in Electronics and Communication Engineering from Model Engineering College, Thirukakara, and MTech in Signal Processing, also from Model Engineering College, Thirukakara. He received his PhD degree in Computer Science from Kochi University of Science and Technology. He has got recognized publications on image processing and remote sensing problems at international levels, including IEEE Transactions, SCI, Scopus Index Journals, and various star-rated IEEE flagship conferences. He is an active researcher in the field of computer vision and deep learning and has undertaken projects under Center for Acquisition for Research Services scheme of the DRDO, Government of India. His research interests include computer vision, artificial intelligence, and deep learning in remote sensing areas. With extreme pleasure, I welcome Dr. Anil Raj to deliver the talk. Welcome, Anil Raj. Over to you.
Thank you, Reena Miss. Thank you, Dr. Santosh Kumar sir. So, very happy to join as a part of the Department of Computer Science family. Let me share my screen.
Yeah, it is fine now. Yeah.
So, my topic is application of machine learning and deep learning in electronics field. So, in this talk, we'll be covering starting from the basics of the signals from the very scratch level. So, what is a signal? What are the importance? What is its importance in this various interdisciplinary engineering fields, and its applications related to this machine learning or deep learning AI fields. And finally, we'll see some applications, some industry level applications of radar data with this machine learning. We will see two applications. in the very deep level. So let us start from the signals. So signal is a flow of information. So we know that to transmit data, it must be first transformed to electromagnetic signals. So which is very important in our in the digital field. So uh, signal is a measured quantity that varies with time, and the electrical signal is received from transducers. Transducers, for example, microphones, thermometers, all this converts the what this physical or another signals to in this electrical form. So mainly signals are of two types: continuous and discrete. So in our digital what in the machine learning or similar type of applications, we are mainly focusing on this digital signals. So in this digital signal takes an discrete value. So it is mainly concentrated on mainly because we can't say all the digital signals are of discrete time, but mainly we can say in a general form all the digital digital signals are discrete time signals. That means values having values in particular time with the labs. So it's a comparison of from the very scratch level analog and digital signals. So let us see what is the importance of signal processing. So this signal processing, the main applications are amplification, filtering, to detect patterns, both in what in the time domain or in frequency domains. And the third one is prepare the signal to survive a transmission channel. So here a concept called modulation came to action. That is, modulation means mixing the signal, the transmitting signal, to a higher level signal to survive the transmission channels. Because we know that today the channel is a very important. So the medium has to split in the base of on the base of frequency. So signal processing, the main important part of transmission is the modulation part, and apart from that, also it prevents the interference with the other signals sharing a medium, so that we can allot a signal, allot a transmitted signal to a particular bandwidth, so that other signals will not be get interference. So next application is it undo distortions contributed by a transmission channel. These are the some of applications. It compensates the sensor deficiencies, find information encoded in a different domain. So in all these areas, machine learning nowadays this AI part or this what machine learning or deep learning is extended to these type of applications. So next, see some of the parameters associated with these signals. So the basic level parameters is periodic and non-periodic. Also, a periodic analog signal, commonly a sine wave, we cannot be decomposed into simpler signal. So its simpler form is the sine wave. So a composite signal is a mix of multiple signals. We can say an example, sine waves. So we'll see that. Sorry. So first one is a simpler signal, a simple sine wave signal. So let's see some of the parameters associated with the signal. So first one, amplitude. So in the top image, you can see having a signal with high peak amplitude, and this second image having is the signal having low peak amplitude. So these two signals having same frequency and phase. So that's the main thing we have to interpret from these images. So these two images having same phase, same frequency, but having different amplitudes. So next one is a frequency. Frequency means nothing but a number of cycles per second, or it's an inverse of time period. So let's see a pictorial representation of two signals having different frequencies. So the main thing we have to understand, the two signals having same amplitude and they are in same phase, but frequency is different. So here, this first signal, in 1 second, 12 cycles have passed. So 12 cycles. So the first signal having 12 hertz, and the second signal having 6 cycles, or 6 periods in 1 second. Cycles means repeating units in a signal. So in 1 second, 6 cycles have passed. So this frequency is 6 hertz. So this is the concept of frequency. So these are the features in in the case of images, like this, in the case of 2-dimensional, 3-dimensional images, the pixel intensities are the fixed frequencies. So the edges, corners, edges, and objects, and connected points, all those are features. But in the case of, in the perspective of the signal, 2-dimensional, 3-dimensional signals, so these are the parameters, some of the frequency components, some of the phase components, some of the amplitude components. Those are the important features. So those discriminating, or those important features, we have to, not by us, that those frequencies, so those features have to learned by the system. So that's the main criteria in the perspective of the signal processing with machine learning. So next one, phase. What is the phase? So basically, there is a relation between phase and the frequency. If two signals having same frequency, then only the component phase has got importance. Otherwise, phase is not having an importance between two signals having different frequencies. So let's see, in a very scratch level, what is a phase. So the first signal starts at time equal to 0, but the second signal starts at -1/t time, 1/4 of the time period. So there is a phase difference of 90 degree. So commonly, the phase of the signal is represented in angles, or in the multiples of pi's. So these two signals having phase differences of 90 degree, and 1 and 3, the third image, the third signal having a phase difference of 180 degrees. So this is the phase differences. So in the case of electromagnetic signals, or in the applications of electromagnetic waves with machine learning, or in a conventional classical type of processing techniques, the importance of phase is very much very important, because the phase has contributed much more in the learning processes. So let's see in the further slides what are the applications, what are the importance of this phase in the coming slides. So these are the main 3 features, or main 3 parameters associated with the signal in the basic signal processing perspective of machine learning. So next, we'll see the frequency domain. So what is the time domain and frequency domain? So in the first image, we can see as time increases, the wave is going on like this. It's a sine wave. So having a frequency of 6 hertz, having an amplitude of 5 volt. So this time, this frequency, this signal is a periodic signal having constant frequency of 5 hertz, 6 hertz. So we can represent this signal in a frequency domain, in another domain of frequency. So in this frequency, we can see frequency domain representation having x-axis of different frequency values, 1, 2, like this. So in the frequency domain, commonly the axes are of frequency with corresponding to amplitude. So we can see that in the 6th frequency, they have a component here. So no other signals are presented in this single signal waveform. So it's not a composite waveform. It has only single waveform having 6 frequency and a peak value of 5 volt. So this can be easily represented by using a single line at a point 6 with an amplitude of 5 volt. So let us see what is the importance of this frequency domain representation in the next slide. So here we have left side. Here in this image, we have 3 signals. We have 3 signals in the same time domain. So one is a signal, a DC signal. DC means having zero frequency. Only 15-volt amplitude is there, so there is no repeating. So it's got a zero frequency component. And second one is of 8 hertz, and the third signal is of 16 hertz of frequency. So these are the three features associated with these three discriminating features. So our aim is to separate these signals. Actually, the main application of these type of problems is in the speech recognition and speech interpretations. Okay, in this type of applications, we have to separate out a single frequency component or single or multiple frequency components. So speaker analysis means very important application in this type of signal processing domain. Speaker analysis. So our brain automatically separates these frequencies. So we are not aware of that. Once we have we talk to a person, that frequency components or that parametric values, that discriminating features are already learned by our brain automatically. So at a very scratch level, we can say a frequency is one of the main component or main discriminative feature of we can discriminate the features, discriminate the signals. So this can be easily separated by using the frequency domain representations. So what is the frequency domain representation? So in the frequency domain representations, these signals can be plotted. We can linearly separate. So in this graph, we can see three signals can be linearly separated by using a threshold value. If we fix a threshold value at 5, we can separate these two signals. And by using threshold tuning techniques, because from these data sets, we can train a model. We can train a model and we can tune the threshold value. So we can fix 2 or 3 threshold values. We can use that threshold values to separate these signals. There is a classical techniques also there, like a Fourier transform of a signal. So we are focusing only on this machine learning concept. So by using these Fourier transforms, we can convert these domains, time domain signals, to frequency domains. That's also possible. So the main aim of this machine learning to improve the accuracies, to improve the automations. So automation is the main concept, main backbone of machine learning, and to adapt new inputs, to adapt new environments. So in this perspective views, machine learning concept is very much applicable for these real life applications. So these are the some basic levels or basic scratch level parameters or features associated with this signal processing or signals. So next, let's see some of the applications of machine learning and in general, in a broad way of signal processing. So I have already said speaker identification. So our brain has an ability to automatically discriminate the features, to automatically learn the discriminating features of different speech signals. So we have to develop, or we have to mimic these type of ability to a system. That's our main aim in the speaker identifications perspective in that area. So this is an old model, very old technique from the scratch level. So it has many data of many speech informations, signals of 10 data. So our model has a capability to extract the features of these sound signals. So the main features are pitch and MF, mel frequency component. So these two are some of the main important features to associate, to discriminate these speech signals. So from these important features, the model is trained, and after training, after perfectly training these data types, we can use this data to discriminate or to identify an unknown speaker. So in a very scratch level. So next one application is activity recognition. So this is also very old type of application, or not old, very commonly known type of application. So we have got many perceptors. So we have an environment with a what agent. We have an agent. AI agent is there. So these agents having different perceptors to collect all the input signals. So here we have this what and glasses to collect the vision, or to collect the to mimic the vision perspective, vision signals, or light signals, and the activities like movements by using these camera, watch, by using these shoes, all the activities. So by using these data, by using all these data, all these percepts, the features are extracted, and a model or deep learning model, or what artificial neural network based AI model is trained, or some conventional techniques are also used. So by using these what informations, we can infer, or we can predict the activity of the particular person, whether he's what in an upstairs, or he's running, he's riding a bike, like this. So we can use these type of signals by using we can use these signals to train the deep learning model for these activity recognition type of applications. So next one is a commonly computer vision. Computer vision means the main area is pattern recognition and pattern classification. So face detection is a very commonly used. Commonly used, no, it's a very important application in this computer vision area. So nowadays, real-time face detection. So in the industrial perspective of face detection, we have used now, I think, FaceNet of 512 landmarks. FaceNet models of 512 landmarks from each face are these faces can be predicted. So this is one of the very good achievement in the face detection area of computer vision. And recently, a new model called ArcFace. ArcFace means ARC, FAC. ArcFace model is an updated version of this FaceNet model. So it has an the updated version means in the loss function. Updation is only on the loss function for the training. So these are the some of the state-of-the-art techniques for face detection in the industrial perspective of face detection. So in this face detection, or in this computer vision applications, the signals are two-dimensional what images. So first, the light intensity. Light intensities are what is encoded, or is quantized to an pixel values. And these pixel values are used to train the model, or used different type of filters, or used can be extended with a machine learning application, with machine learning model for the particular pattern recognition and pattern classification type of applications. These are some general basic layer of applications of signal processing in different domains. So next, focusing on this machine learning applications in electrical or electronics engineering field. So let's see. First one, speed control of motor using machine learning. So in this type of applications, by using some data sets, we can train a model to control the speed of the motor in both forward and reverse rotation with regenerative braking. So in this type of applications, the predictive control is the main useful, important, and very useful in this type of in this area. So in the predictive control, we can control the motion in both forward and reverse rotation. So that if in the case of self-driving cars like AI autonomous cars. So in this type of applications, we can use these type of models or these type of technologies in the motor itself, so that uh, what deviations or what highways or like in the different types of different levels of roads, it could automatically adjust the speed of the motor by using a regenerative braking system. So the main aim of this type of application is to develop a model to get an ability of regenerative braking system. Next one is battery management using machine learning technique. So what is the battery management means? Uh, in the main problem we are facing this battery management is battery use of battery is it's what charging time and what it's leakage time. Leakage means it's draining time. So by using machine learning technique, we can develop a model to predictive maintenance. So that's the term mainly used for this type of applications, predictive maintenance. So we can, by using continuously or by monitoring the timeline of a battery, we can develop a machine learning model or an AI model to control of the battery, like charging time and discharging time, like this. Can use that. The third one is home automation. Home. I think it's very common now. Everybody's known about that area. So, for example, when anybody enters the room, the lights and fans get turned on automatically. So this type of what automations we can make use of machine learning and AI based techniques. Fourth one is fault detection using machine learning. So in the area of electrical and electronics engineering, fault prediction or fault detection. So fault prediction and fault detection are both a different scenario. So fault detection from the history of data or from the current data, whether the product has a fault or it can spot whether the fault has occurred. You can localize this fault of a product, or it can what from the history of data from the product container, we can or the model can be predict the set of faulty devices or faulty products. And next one is fault prediction. So certain set of data or a certain set of products can be built with a fault because of what history of data. By analyzing the history of data or by analyzing the history of products, features of the history of products, this fault prediction is also possible. So this can be achieved by using certain machine learning applications. So some of the these are some of the applications of machine learning. I'm not. These are not techniques. Just some of the applications. And the last one is remote sensing applications connected to machine learning. So the main commonly used remote sensing application is pattern recognition on radar data. So, for example, from the aerial data or from the satellite data, the pattern recognition or image classification or what object classification or object identification is very important nowadays for this in this autonomous or automation in the perspective of automation, and also in the perspective of what security type of applications, security domain. So these object detection or object classification or object identification or the localization of object detection, localization of the objects has got very important in this remote sensing application, mainly in the aerial or satellite image perspective. So these are a very broad area of applications in machine learning in this electrical and electronic engineering fields. So next we'll see some of the techniques that can be applied to radar data. Some of the machine learning techniques or some of the improvements we can achieve by using deep learning or machine learning techniques in the radar data. So we'll be focusing mainly on synthetic aperture radar satellite data. So in this talk, we will be covering mainly two techniques that can be improved. That is very helpful for improving the neural network based deep learning models. That means improvements in the perspective of both time and accuracy. We can achieve real time, or we can achieve fast detecting modules, and with not compromising the accuracy. So we will be discussing mainly two techniques for getting such improvements in the radar signal data. So first we'll see what is a radar. What is a SAR? SAR means synthetic aperture radar. So it's an imaging device. Imaging device means what? Similar to a camera, it's for observing the surface of the planets like Earth or something. Okay. So by using the radar signal, radar means a radar pulse, we can generate, or we can observe the surface of the Earth. So in the satellite-based SAR data, the transmitter is placed on the satellite. So the transmitter and receiver, transceiver. So the transmitter transmits a radar pulse towards the surface of the Earth or towards the ground targets, and the signal will be transmitted, and it will scatter, or it will collide with the target, and some of the signal get lost, and some other signals will be scattered back towards the transmitter. So receiver. So the transmitter and receiver are same in the case of SAR imaging purposes, SAR imaging technologies. So from this principle, from this technology, we will be getting two data. First one is the magnitude data. So this magnitude data will be associated with the intensity of the backscattered radar pulse. Intensity means amplitude. We have already seen what is an amplitude. Amplitude means the highest possible value of a repeating signal. So this magnitude data will be associated with this amplitude. So if the intensity of the backscattered signal is low, that particular area, that means that particular pixel area will be scaled to smaller values. So generally we are getting a SAR data having 16 bits. That means 0 to 2 raised to 16 values of pixel intensities. So next one is the phase data. So what is the phase data? Phase data means the transmitted signal having a phase. So that phase is already known. So after colliding with the target, the phase of the data, phase of the signal can be changed. So the phase can be altered, or it can be changed, and this changed phase data. So this signal is captured by the receiver, and the phase difference is calculated. So this phase difference is also captured by the can be this phase data. Phase difference can be we can interpret from the receiving signal. So these two data can be interpreted by we can interpret these two data, magnitude data and phase data, from this receiving signal. So these are the main two features, main two components of SAR data, magnitude data and phase data. So let's see how we can make use of these two data in the deep learning domain. So some of the information of SAR magnitude information, magnitude data. So I have already said that the magnitude data is based on the intensity of the backscattered signal. So if the intensity of the particular area is high, then the value will be near to 1. Near to 1 means will be lighter. And if it is smaller, I mean, intensity is smaller, then it will be near to 0. Higher the backscattered intensity, rougher is the surface being imaged. Flat surfaces appears at darker areas since most of the incident radar pulses gets reflected away. So if the target is flatter, for example, in the ocean imaging purposes. So ocean imaging purposes. So those areas, what the surface is flat. So the backscattered signals get scattered towards, and it will not reflect, it will not be scattered back to the transmitter. So it gets scattered in different directions. So the most of the data, I mean, most of the incident data is reflected away. So intensity will be very much lost. Thus, these flat surfaces appear more darker. So by using these principles, we can interpret SAR data. Calm sea surfaces appear darker in SAR images. Rough sea surfaces may appear brighter. So these, by using this SAR magnitude data, it is processed to generate a 2D grayscale image. So most of the SAR data are in the 2D grayscale image pattern. So this is an example of an ocean SAR data. So this is a ship. So ship is a rougher area. So most of the signals are backscattered and it is collected by the SAR sensor. So that area is appeared a little brighter, and the ship is discharging some oil into the sea. So these flat surfaces, the signals get lost. So these flat surfaces, appearing as black ring. So this is the way of interpreting a SAR signal, or SAR synthetic aperture radar signal. So next we'll see what is the phase information or phase data associated with the SAR or synthetic aperture radar sensor. So in generally, the phase of a signal. So the phase of a signal may change with two parameters of the target. That is the distance between the sensor, the distance between the transmitter and the target, and then is the dielectric property of the target. So by using because of these two parameters, these two features of the target, the phase of the signal may change. So this is a pictorial representation of the magnitude data and the phase data of SAR image or SAR imaging area. So here A is the magnitude area. So by using by a comparison analysis, we can say that magnitude data have a structural information of the target. So by visually we can interpret the structure of the target. So that's the main thing, importance of this magnitude area when compared to the phase data. In the case of phase image, phase 2D data, phase image, so there is no any structural information of the data. That means the pixel phase in one pixel does not have a correlation, because for each pixels having different phase angles. So there is a phase difference or phase difference component associated with each pixel area. For each area, it contributes some of the some of the phase differences. So all the surfaces, all the targets, all the imaging surfaces, all the minute areas have contributed to some of the this phase differences. So that's the reason why we are not able to structurally interpret the target using a phase data, phase image. So these are the two interpretation of SAR data. So let's see how this SAR data can be make use of pattern in the pattern recognition domain. So today we will be discussing two pre-processing techniques. First, I'm explaining a SARCOM technique. So pre-processing means in the perspective of pattern recognition and or object classification perspective. So not to improve the visual quality of the SAR data, to visually to improve the object detection or object recognition or object classification perspective. So by using this pre-processing, we can we may know ability. I mean, we know we can't improve the visual structural information of the data. So, but the automatic learning of the features, or we can boost the features or discriminating features associated with this SAR data. So the first technique is SARCOM. So what this is the block diagram of SARCOM generation. So first, the SAR raw data. Actually, the raw data having it's a vectorized form of data. It's having first one some of the headers having details of the sensor details, like the time, details of the sensors. So what is the code name of the sensor? Likewise, after this information, after the header values, we will getting a array value of what magnitude data. So if it is generating a 3000 by 3000 images, a 3000 by 3000 pixel of data, so first 3000 into 3000 values will be of magnitude data. After this, we'll be having the phase data. After the pixel information or the number of data will be same for both magnitude and phase data. So from this raw data, first step is to extract the magnitude information and the phase information. Then the magnitude information is normalized to 0 to 1. This is because this is for the deep learning applications. For the convolution-based, CNN-based architectures, we are first normalizing the SAR data in order to generate the first channel of the pre-processed image. So first channel will be based on only magnitude information. Then the second two channels, other two channels are based on phase data. So from the image, we can understand that the phase data doesn't have a structural information of the target. So in order to identify the target, we have to make use of the magnitude information and phase data. So the combined effect will be getting will be yielding much more results. So that's why the phase information is first. The sign of the phase is calculated, and all the pixels are arranged in an array and form the second channel. Next, the course of the phase data is arranged to form the third channel of the pre-processed image. So the 2D grayscale image, is first converted to a 3D pre-processed data. So this is a visual representation of the 3D data. And next thing, this is a deep learning model. Actually, for most of all the applications, like object detection from the SAR data or object classifications from the SAR data, the deep learning models will be mainly focused on extracting the discriminating features. So we have to develop a deep learning model, or we have to design a deep learning model having different filters, different layers. The main aim is to extract the discriminating features of the SAR data. So in this slide, I'm explaining a very simple level of a deep learning model having a having three layers of convolutional neural networks and two fully connected layers. It's a classification-based deep learning model. Actually, this three channels or three layers, I mean, not channels, three layers. Three layers are of depth-wise separable CNN layers in order to make the lightweight deep learning models. So in this perspective, I'm explaining mostly in the lightweight based deep learning model. So because in the satellite or in the industrial perspective of deep learning applications, we can't make use of huge computation for the inferencing. Uh, Everybody knows about inferencing of a deep learning model and training of a deep learning model. So in the case of training, we can make use of high computation data, but in the case of testing or inferencing stages of a deep learning model, in the real time or in the real life applications, we will be focusing on lightweight models having least MAC operations. MAC means multiplication computation application, multiplication addition computations. So these MACs should be least, and of course the model size should be also least. So especially in the case of satellite based applications, the model should be very much least. I mean, having least MACs and least number of parameters and least lightweight. Generally, we can say it as a lightweight model. So in the next slide, I will be explaining how to achieve a lightweight model. So before that, let me explain all the feature parameters or the layer parameters of a model for this type of image classification of SAR data. So this layers are mainly designed by using depth-wise separable CNNs, and one of the parameters is also mostly contributing to the performance speed is the size of the input. So the size of the input should be optimized. So in the case of real-time SAR data, SAR produces normally 3000 or 4000 by 4000 of signal data. So 4000 by 4000 in signal data. So these 4000 images can be directly used. It is not practically possible for the for fetching all the features from these type of 4000 by 4000 images directly. So what as an research level perspective, we can use the patches of that full SAR data. So that's why in this particular applications, the size can be designed to about 300 by 300 size or 400 by 400 size, less than 500 size. So these are the parameters, and it has one more thing. It has a feature boosting technique. Feature boosting means the higher level features are directly connected to the lower level of features. So in this, the first layer, this first layer is flattened and concatenated to the last layer, and the second layer of the output of the second convolution layer, the second depth-wise separable convolution layer, is flattened and concatenated to the second last fully connected layers. So these type of techniques are known as feature boosting technique. So this also improves the accuracy in the perspective of the lightweight applications. So the main problem of these lightweight deep learning models is, of course, there is a lesser number of filters. There are a lesser number of parameters to learn the features. So there might be having this accuracy drop. So we have to do some more researches on improving these in compensating these type of accuracy losses. So that's why we have I'm proposing these type of pre-processing techniques and these type of feature boosting techniques. So the deep learning models doesn't have only the capability of feature extraction; it should be having capability of the feature boosting techniques also. Then only it is practically possible in these real-time applications. So next, we'll see how to design or how to achieve a lightweight deep learning model. So I will explain a simple technique you can follow. Or I can't say this is a standard technique, but these are the techniques I am following both in industry-based applications, also in the research level applications. So first, we have to optimize the pre-processing technique. So this first table. So first we have to fix the evaluation indexes. like what all are the metrics we are using, what all are the evaluation metrics we are focusing for this type of application. So this is a classification based model. So I am fixing recall, precision, F1 score as the accuracy parameters. And next thing, parameters, model size, and FPS. Parameters means number of parameters, number of weights. So these number of weights, model size in the hard disk models in MB, and FPS is the frames per second, speed, performance speed. So these three parameters, these three values, these three evaluation metrics are fixed for evaluating the performance speed. So there will be a trade-off between these two accuracies and this type of speed. So first we have to analyze what all are the we have to optimize the pre-processing stage, and PP stage is the pre-processing stage, and FF is the feature boosting or feature fusion stage. So if whether they are contributing a lot for this type of accuracy trade-offs. So this is the technique. I have tried with all these techniques and found FF stage and PP stage is very more contributing towards the performance speed and performance accuracy. After that, we have to design the kernels, or we have to design the backbone network. So backbone means to design the number of layers, or design the layers that has a capability to extract the features from the input data. So in this stage, we have to first keep in mind, first thing is we have to not only capture all the features. So instead of capturing all the maximum features, most important thing is to capture discriminating features associated with the classification or detection. So what are the main important features? So in this type of research, we can try with the pre-trained models, all the trained models, and we can draw a benchmark. So in what all areas these type of data we are getting these accuracies and speed. After that, we can select a model, and from that base model we have to work on designing least number of kernel parameters. So the number of kernels is a very important parameter in order to make the model lightweight. So in this proposed model, we are using first layer having 32 kernels, second layer having 64 kernels, and next one having 128 kernels. So this kernel patterns, or these filter patterns are optimized only after a certain number of researches. So we can make use of different trials. First one, we can start from the lowest trials, and we can keep on increasing. And after that, we have to find an optimum value. Then we have to change the filter patterns among them, and we have to calculate all these values: recall, precision, F1 score, that is accuracy values, and performance parameters. So from all these researches, we found that these patterns having 32, 64, and 128 patterns. So this pattern having highest accuracy and highest speed, highest performance speed. So the main conclusion from this type of researches is, in order to capturing maximum features, the important or the most
Dr. Anil, there is a problem with your mic, I think. Hello?
features, these FP reduction is one of the main important we can avoid those type of FP's reduction, and of course we can improve the accuracies. For example, in the case of automatic lighting conditions, so in the cameras, we know that in the cameras it has an automatic lighting. In the night conditions, cameras having lesser number of light provides lesser number of light in the what in the screen, in the imaging screen, and the daytime the brightness will be lows in the camera applications. So these type of applications, the FPs will be much more much more problematic in the case of real time applications. If FPs means I mean predicting or detecting light. If FPs means actually there will be no light, but the model predicts it as a light. So the light, so the intensity contributing by the camera will be lesser. So these type of FPs is very much we can avoid in the designing of deep learning applications, deep learning models. So by using these kernel level pattern designing level of researchers is very much helpful for those type of applications, introducing FPs.
Dr. Anil,
Sir.
yeah, I think we can take a short break.
Okay, sir. Okay.
Yeah, maybe 10 minutes break we will take, and you can rejoin after 10 minutes.
Okay, sir. Okay.
Yeah. Participants, by the way, if you have any questions, you please make a note of that. We will ask that during the last spell of the talk. Thank you. We will have a 10 minutes break now. Yeah. Yeah, Dr. Anil.
Yes, sir.
Yeah, we can resume if you are ready. Yeah.
Okay, sir.
Yeah.
Let's continue to the second technique of using radar data to the deep learning model. So I think we have already understood the previous technique very well. So let us move to the second technique. So in the radar data, the main problem associating with this radar data is discriminating features are so small and minute. So in the case of normal images like face recognition, object detection, human detection, human post estimation, in these type of applications, the objects are um having a relatable size with respect to the frame of the image. But in the case of SAR data or in aerial images or remote sensing data, so these discriminative features of these size of the object will be so small compared to the size of the image or frame of the image. So that's why we are using these type of dedicated pre-processing techniques to improving these quality of these data. So in the case of normal images like 2D images, we can't extend this normal noise reductions or what image filtering or quality improvement techniques to these type of signal data. The main problem is these normal pre-processing data may have the ability or may destroy the discriminating features. So since these discriminating features are so small, we can't directly use these type of what classical noise removing or quality improvement techniques that are already applying to this normal data or normal RGB images. Uh, color images, we can't extend these type of applications to the SAR data or radar signal data. So that's why we have to focus on the processing data, and we have to focusing on improvement of this quality of the features of the radar data. Also, in the perspective of what industrial perspective of deep learning applications like auto focusing applications of the camera or what lighting additions of the objects. In these type of applications also, we have to design a pre-processing. So I'm explaining that pre-processing technique has a very good importance in this type of deep learning applications, because we have to teach the model the important features. That's the important. So instead of teaching wrong information or redundant informations, we have to teach the model the apt informations, the important discriminating informations. So these important informations can be boosted by using various pre-processing techniques. So custom pre-processing techniques will be having very good accuracy in the perspective of final accuracies. So by continuously monitoring the final accuracies, we have to redesign the pre-processing techniques according to our need. So that's the basic technique of this deep learning model designing in the industrial perspective of applications. So let us see the second technique. So here we are only using the magnitude data of the SAR data, magnitude information of the SAR data. So we are avoiding the phase data. So let us see how this magnitude alone will be giving good results by using a custom pre-processing technique. So initially the 2D raw SAR data is pre-processed to generate pre-channeled SAR images to improve the quality of SAR data. So here from various experience, we can understood that we can interpret that learning from different channeled data, different structured channel data will be giving more important, more accuracies in the perspective of accuracy and also what speed. Speed means frames per second or what performance speed. So by creating, instead of giving the normal image, instead of giving the raw data directly, we have to generate more channeled data by using certain techniques, certain image processing or certain similar what signal processing uh, informations, signal processing techniques. We have to first generate multiple channel data having different information in different channels. So then the model can be able to learn appropriate features of these different channels. So also in the perspective, in the real life applications also, if we are provided with more data, if as a human we have to, instead of instead of learning the features of a particular object, instead of seeing or instead of capturing the features directly, uh, study different patterns of the data. Instead of studying same patterns of different time, we have to study different patterns at different intervals of time. We may able to get more information from the data. So in the similar manner, the model we have to teach the model having different information in the different channels, and will be improve the accuracy, or will be improve the performance of the model very much higher level. So let's see. Let's name these channels as CA, CB, and CC. So we are provided with the raw data of 2D channel, only one channel of 2D data. Okay, only one channel of 2D data, and we are generating a preprocessed data having three channels. We can name as CA, CB, and CC. So for this process, we are extending the application of Lee filter for despeckling. Actually, in the SAR data, the main problem or main noise that may occur due to the scattering purpose of due to the scattering imaging technique is the speckle noise. So speckle noise, we have to instead of directly using this Lee filtering, the speckle noise reduction techniques. Instead of if we are using the speckle reduction techniques directly, they might destroy the discriminating features. So that features might get lost, because if you're using blurring techniques, or if you are using adaptive blurring or like techniques, that might destroy the features. That means the features of the objects might be destroyed. So we can't use directly these type of classical filtering techniques in the case of radar data or signal type of applications. But in the case we are making use of the application of the leaf. So let's see how this is used. So here first the SAR data. From the 2D SAR data, we are generating three channels. First channel is the same data. Same data means to perceive all the information without even destroying minute details. Uh, we are just using that same raw SAR data as the first channel. And the second channel we are fixing as a Lee filtered version of this raw data. Lee filtering means it's a famous filtering techniques to reduce the speckle of SAR data. Not only the SAR data, all the speckle noises of different filters, like X-ray scanned images like this, lidar scan images, like similar images. So these images, Lee filtering actions, all the actions, all the applications of Lee filtering reported very good accuracies. So that's why we have used or we have designed this Lee filtering as a speckle removing agent of this preprocessing stage. And the third channel is the Lee filtering plus image inversion type of processing. So this image inversion is defined or is developed based on, in order to reduce the effect of background. So image inversion means all the zeros will be 1 and 1 will be 0. That means in the case of 2D, 8-bit images, highest value will be 256. So find the what differences to highest possible value of the pixel value to the Lee filter value. That's the image inversion. That means 255 minus pixel value of the image. That is the image inversion plus a Lee filtering of the original SAR data. So this is a 3-channeled pre-processing SAR data. It seems to be a very simple pre-processing technique, but we are getting a very high contribution towards the accuracy improvements. Because instead of using the SAR data or the signal directly. We are just generating three multi-channels having different information but correlated information. It is a correlated information. But learning from these correlated informations, we are the model will be model will be conversed much more faster with higher validation or evaluation metrics. So I'm only explaining one technique, but while designing various deep learning applications, we can think in this way of designing pre-processing techniques. So let me explain the parameters. Leaf filtering means CB might equal to S bar plus W into S by. You can explore these in the original paper of the leaf filter. So this is a pictorial representation of the generated SAR data. So this is the original SAR data. So first channel will be the same SAR data. Second channel is the leaf filtered version, and third one is the image inverted version. Image inverted version of the leaf filtered version. So this is a visualization of some of the SAR images, SAR vignettes. SAR vignettes means these data set is provided for the weather prediction type of applications. So I'm not showing that results. Instead of that, you can explore the papers. So anyway, we have already seen two different pre-processing techniques in the different perspective. First one, we have seen how multiple data can be combined to improve the accuracy of the deep learning or ML type of applications. Next stage, we have seen how the single data means only the macro data can be used to generate multiple informations. So in this way of thinking could improve the accuracy perspective and also the performance speed perspective also. So these are the some of the papers I have already explained. So the first one is SARCOM is based on a ship classification type of application, and also this SARCOM is also used in this ship detection. Detection means localization of the ships from the SAR data. And the second one, the second application, that is pre-processing technique 2, is based on SAR vignettes classification type of application. And these are some of the references. So any doubts from the audience side?
Yeah, participants, if you have any questions, clarifications, you can unmute yourself and ask. So, Dr. Anil Raj, you were actually stressing a point in throughout the discussion that must reduce the false positives, right?
Yes, sir. Yes.
Yeah. To reduce the false positive, you are concentrating on the pre-processing techniques, right?
Yes. Yes. Yeah.
Okay. And in deep learning, we usually await that the deep learning model itself learn something from the given data, right?
Yes.
So, is there any advantage of adding our traditional kind of feature learning techniques with this? Usually, we supply data in the deep learning model, and it itself learns features, right?
Yes.
But here you are concentrating on more on the features, right?
Yes.
So, any traditional kind of feature learning techniques will improve the model, or what? What is your opinion?
Actually, we are not focusing on this feature boosting. We are just improving the accuracy by using several combinations of the input patterns.
Okay, okay,
Yeah.
okay.
So
Yeah.
we are not focusing on the features directly. So
Hmm.
explicitly, we are not focusing on the feature improvement,
Yeah,
but
yeah,
certain patterns or certain but combinations of the data might be improved. The accuracies in the perspective of the false positives also.
yeah, yeah, yeah. Now I got it. Yeah.
Okay.
Yes. Okay. So multimodal, or I mean multispectral kind of features, or those type of things will give more advantage, or
Yes, yes. From the experience of different designing or levels of deep learning models, I can conclude that
yeah. Okay.
establish that type of applications.
Yeah, yeah, yeah. Okay. Fine, fine. Yeah. Yeah, it was quite interesting because you were concentrating on a particular work. I think you might have done a lot of work in this, but you were able to discuss it. Uh, some noise is coming. Yeah, okay. So you were able to discuss, and I mean, you were able to present the given problem in a very elegant manner. So thank you for that. Yeah.
Thank
Eh,
you, sir.
yeah. Any other questions? If you have, you can ask.
Hi, Anil. Dr. Shailesh here.
Hi, Dr. Sailesh.
Yeah. Uh, I have a general doubt.
Okay,
So,
sir.
usually, while dealing with electronic signals, we are mainly uh, the depends on two different approaches. Like we can directly process the signals. Otherwise, you can make it into some spectrogram, frequency domain signals, and process it.
Yes, yes, yeah.
So, which one is more preferable, and which will give more results, good results?
Yeah, yes, yes. Nice question. Actually, in the perspective of electronic signals, if we focused on the time domain signals, that means if we are dealing with the real time domain, real time perspective of applications, we can't we can what we can convert the history of data into episodic signals. So in our work also, in our industrial based work also, we are dealing this type of what real-time signals. So these real-time signals can be converted to different episodic forms. In that type of applications, we can, from different experience, I can say that frequency domain or phase-based domains will be much more, in the perspective of accuracy, much more useful in the perspective of accuracy and speed also, because time domain more repeating values will be there. Time domain repeating in the in the what as a cycle form, more repeating components will be there. So more redundant components will be there in the time domain. So these redundant components can be avoided by using this frequency analysis of data. So by using these episodic data, first we have to convert to phase domain or frequency domain. That will be more useful in the case of electronic based, or I can say electronic based signal processing based applications.
Okay, thank you.
So, any other questions? Any comments? Yeah. So, if you don't have any questions, maybe let us together thank Dr. Anil Raj for his very focused work presented today, and especially concentrating on the quality of input data rather than quantity. I think in the last two presentations also we were listening to this. Quality of data is very important. So Anil Raj also by today's presentation, he was stressing on that point as well. So let's join hands to thank Dr. Anil Raj for his excellent presentation. Thank you, Anil Raj. Somebody wanted to make some comment?
Thank you, sir. Thank you.
Sir, can you share the materials as we have an assessment tomorrow? All the materials till now.
Material in the sense
The slide, the presentation slides and all.
Yes, we are collecting it from the resource persons. We will send it to you soon.
Because tomorrow we have an assessment, isn't it? That's it.
Yes, sure.
okay. Okay, I think we will contact all the presenters and get the whatever material that they wish to share with us. Definitely by maybe by tomorrow morning itself, we might be able to share some materials. Yeah.
Thanks.
Okay. So thank you, Anil Raj. Thank you all the participants. Have a nice time ahead. Good night. See you tomorrow. Yeah. Bye.